In case of compound pendulum, the formula that we wrote was torque equals to so like sort of pendulum. See, point of suspension. This is center of mass, and the distance between the point of suspension and the center of mass, we call it L by definition. L is called the length of pendulum. And if you tilt it, by some angle theta, we keep theta pretty small, but for the sake of illustration, we do like this. And why we keep it small? For the obvious reason, we want the linear relationship between the angular displacement and the angular acceleration. So this is L. So torque about O will be mg multiplied by this length, which is L sin theta. So you can see that torque is not proportional to angular displacement, but it is proportional to sine of angular displacement. But we do not want this relation, so that's why we keep theta small. Because if theta is very small, then sin theta is as good as theta. So the torque you can write as mgl theta. This will make this SHM condition fulfilled. So the angular acceleration will be, because theta will grow this direction, but alpha is in this direction. So they are opposites. So that alpha is minus tau restoring upon moment of inertia about O. This is how we write, isn't it? So this will be minus mgl upon I naught into theta. Or you can compare with minus omega square theta. If you do so, then you will get omega square equals to mgl. Now, L is something definition, so you should not confuse with L when it is given as a dimension to for rod of length L. So that L, this L is different, and therefore the time period terms have to be 2 pi and the root. So this is a very famous formula for the this what is it, compound pendulum or physical pendulum. Also, in case of uh, in case you don't know I naught, you know ICM, you can apply the parallel axis theorem. So I naught we can write as ICM plus ML square, and in general, if we write ICM equals to the MK square, because K is the radius of gyration. So the I naught becomes really nice formula. It's M K square plus L square. And that is where you can realize something, that it is independent of mass. So it depends on mostly geometrical property. So we may replace I naught by this formula, and then we have MGL and this we can write as a square plus L square divided by L whole upon G. And what is interesting here that this will give you like something like a simple pendulum formula L effective by. So the formula is quite similar to the simple pendulum with a difference that the L effective value.
So what is L effective?
I mean the effective length of equivalent simple pendulum. So you can replace this by a point mass and imagine the L effective as this much value. So what is L effective here? To compare the formula, L effective is K square plus L square by L, right? You can see this value. This is L effective, which means every physical pendulum of situation like when the separation between the center mass and the point of suspension is L, this is equivalent of a simple pendulum, and the mass we can think as a point mass with the length L effective, and the L effective is this much value. This is the meaning of you can replace any problem of compound pendulum by imagining this problem. Understood? So here the string of length we assume L effective is equals to this value, and what we can see the L effective is K square plus L square by. So now L effective is how much? K square by L plus L. Okay. Now if L tends to infinity, the L becomes infinite, right? So let's do some mathematical. So if I plot the graph between L effective versus actual L, the L is the separation between the point of suspension and the center mass. So when L tends to 0, the L effective becomes infinite, right?
Yes.
Mhm. And when L tends to infinity, the L effective is also infinite.
Yes, sir.
So somewhere between it must be minimum. So let's say this is the L L mean, which gives you the L effective also minimum. So this is the minimum effect. This is not L minimum. This is just L values for it.
L minimum, yeah, sir.
Just name it L. So the L value for which the effective length is minimum will give you the least time period or the quickest oscillation. So it is a very famous and common question that for any physical pendulum, how we must suspend to minimize the time period or maximize the clicking speed. So to find the L minimum, effective minimum, so you can think this way. Let's say this is X and this is Y. So this equation we can convert into Y equals to K square by X plus X. And we know for Y minimum, we can use the calculus dy by dx equals to 0. And if you differentiate the function, what you get? Minus K square by X square plus 1 equals to 0. Which will give you X equals to K. Which means if the L is equals to K, then this will be minimum in value. And therefore the minimum value of L effective is k square by k plus k, which is exactly 2k. So this is generally asking the examination, what is the minimum time period of physical pendulum? The answer is 2 pi under root 2k by g. Is this clear? And k is the radius of gyration. Is this clear, guys? No.
Yes, sir.
Okay. So let's say we have a rod. We'll take a start with the rod of length L. Now, just to confuse you, this L is nothing to do with the L in the formula. This L is simply the dimension. You need to think about L separately. So we can say that the center mass is here. So to find the radius of gyration, what we can add? ICM equals to mk square,
MK
which is
square.
ml square by 12 equals to mk square. So k turns out to be L upon 2 root 3. So 2k will be equals to L by root 3. Nice. Okay, so where we must put the suspension? So we know that the answer is for the point of suspension, the L must be equals to K, that is the center mass and the point of suspension must have this relation. So if you put this is the point of suspension, and if this is exactly equals to K, then this rod will perform
Minimum.
minimum time period, and the T minimum in that case will be 2 pi under root 2k by g, which is like 2 pi under root L by root 3g. It is clear?
Yes, sir.
Okay. So let's say if I give you a disk, let's say we have a disk and we want to suspend somewhere. This is the center. So this is the point of suspension, and given is this is R by 2. So this is the axis of rotation or oscillation. So here I'm not asking minimum. What is the time period? So given the radius is capital R, and it is mentioned it's a disk. What is the time period?
2 pi root under 3r square by 4gr.
So 2.0 root. So you can find there are two ways. You can write the formula I naught by mgl.
हाँ,
That is easy in situation like this. And the moment of inertia is pretty much simple. We know m r square by 2 is about center mass plus m r square by 4 in parallel axis theorem. And the L is the separation between the point of suspension and the center mass, which is r by 2. So what you get here is m r square. So r plus r by 2, which is 3r by 2, right? This is the answer.
3r by 4g. अच्छा हाँ ये बात
Hmm?
हाँ सुन
No. So you can solve any problem using the formula. It's pretty easy. Before I wrap up this part, you can just solve this question. So we have two rods which are joined to each other and welded together. So they should behave as one single rigid body. And the angle between them is 90 degrees. The length of each rod is L, mass is small m. Even though I will not give you mass to solve this question, but yeah, it's given to me. And it is suspended very nicely at the vertex like this. So at equilibrium, we can understand the center mass will be below the point of suspension. If I give a small tilt, it will start oscillating. And the question is, what will be the time period of oscillation? That's it. So try this out, then I'll help you. Okay. Take 2 minutes, and then 2.5 minutes.
So 2 pi root under 2l by 3g.
2 pi root under
2l by 3g.
no, I don't think so. So what is the L? What is the L here? L of pendulum.
So
What is the length of pendulum? Because unless
L
you will
only.
not,
Sir, L only.
how L is L, that's impossible. L is called the length of pendulum. And what is the definition? Separation
Distance from center.
between
Separation from hinge to the center of mass.
so where is the center mass of the system? It is in between the middle point here. So center mass of each rod is here and here, and then you can take the center mass of these two. And this is L by 2. This is 45 degrees, so I can say this is L by, oh, sorry, not this. This will be, the height will be how much? L by root 2, 2 root 2. So basically, the L in this formula, the length of pendulum is length of pendulum is L by 2 cos 45. Do you realize this? You will not. And the
Yes.
formula says the time period is 2 pi under root 2. Moment of inertia. What is the moment of inertia about
L by
O?
G.
ml square by 3 into 2 times. So for the rod, about the end point, it is ml square by 3, but we have two rods, we can multiply it. So I naught is this much by m of the system, which is 2m, g l. So what you have is anything but the answer. So time period is so there is no realization. You're not realizing what I'm explaining again and again. Don't be a blind problem solver. Realize the term what we try to write here. 2m will cancel out. So L square by 3 G L by 2 root 2. So this will be, so you must have made mistake somewhere in finding the L value, this one, right?
Yes, sir.
So you can solve any problem. You just need to be careful about how to find the L. In fact, this problem is so easy. You can also do it by the very fundamental method by tilting by theta, finding the net torque, writing the equation. You can get the answer that way also. In fact, I will encourage you to solve from the scratch. So try solving from the scratch because this is the diagram. After tilt, it will be like this. So center mass will be here. So you have to find the net torque about this because this will be farther, so it will have bigger torque, small torque, big torque. So net torque is the difference of the two. And then equate with the I alpha, like I naught into alpha, then progress accordingly. So can you try by the scratch method? Like, just I want to see whether you have learned this concept or not. So anybody who is interested in solving this from
Sir,
scratch?
I'm sorry.
Hmm? No, not interested.
solving.
Okay, good.
So I'm getting 4 root 2 L by 3.
No, answer cannot change, right? So you're getting 4 root 2 by
3.
So just let me confirm. Hmm. Yeah, fine. This is the right answer. So anyway, this is the vertical and the suspension line. What you do is you will tilt this rod. So this will become let's say 45 minus theta because we're tilting the theta on the right side, and this will become 45 plus theta because the angle is 90 only, right? Gravity will act at the center of mass, and the distance of the point of application of force to the point of suspension is L by 2. So net restoring torque will be equal to mg L by 2 sine 45 plus theta minus sine 45 minus theta. Hmm? So you can do sine C minus sine D, or you can expand and solve the way you want. Which one? Sine C minus sine D.
D.
So what is sine C minus sine D? 2 cos C plus D by 2, which is 45,
Cos 3.
Sine C minus D.
which is theta, right?
Yes, sir.
So this will cancel out. We are left with mgl by root 2. And for a small angle, we can write as theta only, right?
Yeah.
So mgl by root 2 theta equals to I naught alpha, which is 2 ml square by 3 into alpha, correct? So alpha turns out to be minus 3g by 2 root 2 L. So we are getting the same answer.
So I didn't understood why it is 45 plus theta.
So in the beginning, what was the angle between the vertical line and the rest? This is 45, this is
What?
45.
Yes.
So if I tilt but slightly, if it is goes this way,
Yes, sir, understood.
okay, yes, good. So now, okay, fine. So the rest is simple. But the formula is pretty fast. If you can understand the basic, you can get the answer quickly. But it is always good to know the scratch method or the torque method. So you may get a question something like this. So we have an object of dimension. I can just think of two rods which are attached like this. in the L shape, each with mass and length L, and we are suspended from this end, oscillating in the plane parallel to the plane. So, what is the time period of a small oscillation? Do this question. This is pretty easy. You can solve this. Either you want to solve by the basic or the way you want.
Constant.
So 2 pi root over 79 by 90.
79 by 90. Okay. So first of all, I will do the I naught calculation, which is ml square by 3 plus
ml
ml
square
square
by
by
12 plus ml square.
which is same as no ml square by 12 plus ml square,
ml square.
correct? This turns out to
17
be
ml square by 12.
okay, so 12 and then 4 plus 1 plus 12, right? Correct. 17 by 12 ml square. What is L? The
3L by
length.
4.
So
Yes, sir,
length.
3L.
So this is M here, and this is M here, right? This will be somewhere here. So from the point of suspension, it is 3L by 4. That's the right answer. So time period will be 2 pi under root I naught by M of system, not 1M.
Oh,
G.
sorry.
So I got the same answer by doing the uh, scratch method. Yes.
Very good. That's better. So 2 pi under root 17L by 12 into 2G into 3 by 4. No? 2 2s are 4 and 2 6 is 12.
17 L by 18.
Yeah, 17L by 18G. Eh?
Yes, sir.
Right. Very good. So of course you can do it by scratch method. You just find the torque and get the answer. That is, in fact, sometimes it is scratch method is easier than using the form. So always use the method which you understand. So now this problem is again very famous. You will come across very often. So if we have a circular path, maybe like this. Do the center first. So you can see this is the center of this curvature. The path is a circular path of curvature of radius capital R. So you may take a cylinder which is kept at the bottom, then at bottom it will be rest. Friction is sufficient to prevent slip, any slipping. Friction is sufficient to prevent any slipping. So we are going to solve the pure rolling question. Now, if you move this object either right or left, it will come back, right?
Yes.
So if I move it slightly ahead, maybe if I move by a very small margin, very small angle theta, then it may behave as a SHM also. So question is, what is the time period of oscillation? So you can start solving by the scratch method. Then I'll give you the other form.
So
So first
mass
do it.
M.
Yeah, mass doesn't matter, but you can take it. The radius of the small, yeah, what matter is the radius of this small cylinder. So it is smaller, and you can think as a sphere, cylinder, disc, whatever. So keep it. What to keep it here is consider ICM equals to mk square. I want the answer in terms of in general k, because I don't want to derive for cylinder or disc or something. I want to derive for any shape object, circular cross section. So I'm going to use this formula. So that will be true for ring also, and so on and so on. Try this out now. So from scratch, it's pretty easy. And for a small angle, everything will be linear, and so you can get a SHM relation.
So I got time period as t is equal to 2 pi under root
Hmm.
K square plus R square by GR,
Which R? Small or capital R?
capital R,
By?
GR.
No.
So I got capital R in the denominator.
Tell me the equation which you wrote at angle theta. So at angle theta, what you wrote? Because it will try to come down, right? So we can we can do the ABD here, and if you do the ABD, then friction will act like this. This will be static friction. In normal will act like this of no use, but this is of no use because we are not dealing with the limiting friction. And gravity will have a component down the plane. And this way also. This will be mg sin theta, right? You can see it here. This will be mg cos theta. Okay. So mg is acting like this, no? This is mg.
Yes, sir.
This is theta, right? So mg cos theta. So the net force down the plane is how much? So net force down the plane is
Minus F.
mg sin theta. Yeah. Mg sin theta minus f s equals to mass into acceleration, right?
Yes, sir.
And to get fs, we can use the torque relation. So fs into small r, the torque about into mass, equals to ICM into alpha, right? And because it's pure rolling, so A equals to alpha. We have done this in chapter before. Mg sin theta minus fs, which is ICM alpha by r, right? Fs equals to, yes. So this turns out to be mg sin theta equals to ICM, and alpha we can write as A by r. So this becomes A by r square plus m. So in fact we know this answer, but I'm just rewriting the same. So if you know the formula of acceleration, this is done. So at angle theta, this is the acceleration, and yeah, so that is g sin theta upon 1 plus ICM upon mr square. And you know ICM, this is answer known to us. It's k square by r square, right?
Yes, sir.
So we are done. Basically, this is the answer which you should have known. Just for practice once again. So what you see here is that the acceleration is g sin theta and 1 plus k square by r square. We are writing the value, the magnitude. But if you want to write with sign, you can put a minus sign because theta and a are opposite. Now the question is how to write sin theta. So if I say this as x, the gap as x, then sin theta will be how much? So the center mass is moving, right? So center mass is how far from the O? It is
R plus
r minus small r. Right? The separation from the center mass to the point of suspension is how much? Capital R minus r. And if you write the x, so you can write theta equals to L by r. Understood? This is how we can write theta. And therefore, this we can rewrite as minus g x upon r minus r into 1 plus k square by. And therefore, if you compare with the minus omega square x, the omega square turns out to be g upon r minus r, 1 plus k square by r square, and time period becomes 2 pi. It is clear?
Yes, sir.
So let's say if I say for ring or hollow cylinder, you can easily write the answer as the k square by r square will be how much? 1:1.
Yes, sir. Yes.
So the time period becomes 2 pi under root r minus 1 by r pi. So that's the ring. You can do it for disk.
2 r minus 1.
Pardon? 2, yeah. So for disk, it will be how much? 3 by 2.
So, yes, sir. 3 by 2.
So you can keep on doing for other shape also. So any oscillation of a rigid body will follow the compound pendulum concept. Any oscillation of any rigid body. Okay. So now we can do the SHM in gravitation, or we can do torsional pendulum. First, let me finish the pendulums that we know. So we have torsional. You can check the spelling. I'm not sure. Maybe okay. Neither double S. It's single only. Okay. So let me draw a disk first. This is a disk, and we have a thin rod. We will show it by some dimension. This is like a ceiling, or I don't know. So even if you look at this part, this will have some radius smaller. And the radius of this, let's call it capital R. So capital R is definitely much bigger than small r. So just imagine a line. I mean, take any line in the disk, and imagine you are twisting the disk by a small angle theta, so it will vibrate or oscillate. So it will oscillate between this. So as if I tilt by or twist by theta, it will just vibrate like this. It will perform the angular acceleration. Okay. Now, as you twist the disk, the rod from which it is suspended will also get a twist, isn't it? And we know that when you twist the rod, what will happen? It will create the restoring torque. So a twisted rod will try to come back, and so the disk will be also trying to come back. So the torque due to the torsional constant is proportional to the angle of twist. The restoring torque will be proportional to the angle theta, and if you equate with equality, it is c theta, where c is called the torsional constant. And I hope you remember the c value, which is pi r power 4 eta by 2l, right? This was the formula. And eta, this comes from the modulus of rigidity. So in case if you don't remember, I can derive it. I know the formula. So, yeah, it's the length of the rod.
So it is oscillating sideways.
Pardon?
So how it is oscillating? So I'm not able to like visualize.
Don't visualize. It. This is the formula. So this we derive in the chapter of elasticity. So if you have a rod, I hope you remember the rod. So
Yes,
the
sir.
top is fixed. If I tilt, so this is fixed. So if you twist the bottom, it will this point P will come to P dash,
Yes, sir.
and this is called the shear strain,
Yes, sir.
and the shear strain is the displacement which is R phi. Phi is the twist angle. This is the twist angle upon L. This is the and then the force is defined as okay, everything I've written. So you have to think of a hollow cylinder, then derive the formula force upon area, which is 2 pi r dr upon equals to eta into shear strain, and then okay, this theta is different from this theta. This is the twist angle. So phi. I have taken theta here twist angle, but there it is phi. So okay, you can derive like this, and if you don't derive this, you just remember the formulas. The torsional constant is equals to this value. Okay. So a twisted rod will try to come back into the original position, and so it will take the restring torque. And because the rod is fairly thin, so the moment of inertia of the rod about this vertical line will be how much? Zero, isn't it? So what is the moment of inertia of the system about this axis, vertical axis? Because it is turning this way, no? So what is the moment of inertia? So I will be I rod plus I disc, but I rod will be tending to zero because thin rod. So in fact, if you want to connect like this, if you connect rod as like a cylinder, rod is like a thin cylinder, and the formula is how much? It's a almost negligible mass. So if I say this mass is m and its mass is capital M, just to distinguish, if the general way of writing will be m r square by 2, which is like a disk formula, I mean thin cylinder formula, plus capital M capital R square by 2. But we know that this answer is negligible compared to this answer. So the rod is let's say massless or almost zero mass compared to this. So we take this as 0, and so we can write as a mass square by 2. Or if they give the mass, then you have to add everything. But whatever they give, I mean, I really don't care. What we can solve is that the alpha is minus tau restoring upon moment of inertia of the system about the vertical axis. And so the answer is minus c theta by I about the vertical axis, and we can compare with minus omega square theta. And so the where should I write? Okay. So omega square is c by I, and so the time period is 2 pi under root I by c. So this is the very famous answer. One should be aware of this. Okay. What is next? So anyone having any doubt in this? Please do ask.
No, sir.
So the next part is SHM in various other chapters. So let's say SHM in gravitation. We can also learn. So that will be like slightly complex for you guys because I haven't taught you gravitation, but I expect that you know the very famous Newton's law of gravitation. So let's say if we have Earth, which color Earth you want? Blue, green, or orange, or any color is okay. Okay, assuming all colors are okay. So let's say we have the Earth of radius r. So what is the formula of G on the surface of Earth? G on the surface of Earth is Gm by
R square.
r square. Now, if the density is rho, let's say the Earth is a homogeneous sphere. If the Earth is homogeneous sphere, we can write the density equals to mass upon volume, which is 4 by 3 pi r cube. Now, density is a term in which we generally express the answer because density we take as a fundamental quantity. And okay, here it will be r. So this is the G on the surface, on Earth's surface. So on the surface of Earth, we write like this. And so G we can write as and you can see G really depends on the mass is not fundamental because mass we can write as density to volume, but density is like independent of the size. Density is just a point value. You can see the answer becomes 4 by 3 pi rho G. Now, in fact, if you want to find the G value at any distance r, so finding the G value at a distance r is as good as finding the G value on the surface of Earth of a radius r, isn't it?
Yes, sir.
So G at a distance r from the center will have the formula 4 by 3 pi rho G r. That's it. So this formula is really helpful. You can easily remember the answer. 4 by 3 pi rho G r is the answer of the G at any distance r from the Earth center. So this is the answer from the center of Earth. We do not apply this formula for the away from the Earth. So if I go here, I cannot apply the formula. The reason is this part is having no mass, right? And so the answer will be different. So for anything beyond the Earth, the G will have a different formula, and what it follows is the formula G at a distance r more than re is only true for this domain. But if r is more than or equals to re, that is beyond Earth, the formula becomes Gm by r square. Okay, so this is r square, and therefore the r will matter. How far is the r? So you will get the answer very in a very complex answer, like you can get G as G by r square density into 4 by 3 by r cube, and you can see that it will not cancel out. So the answer will remain in terms of 4 by 3 by rho G re cube by r square. That's the answer. Even if you want to write in terms of uh, in general like this. So it will not cancel. For inside we have a nice formula. Okay. All right. So let's say I believe that you understand the formula of G at a distance R, and what next? So let's say inside the Earth's surface you dig a tunnel. So you can dig a tunnel the way you want. No one is going to stop you. So I randomly make a tunnel like this, and I'm assuming that the distance of the tunnel from the Earth center, the perpendicular separation between the tunnel and the center, is D. Okay? And let's say we have a toy train, or maybe some a train which the Musk is making, so which will travel from one end to the end of the tunnel easily without much effort. And the train will be propelled by the gravity itself. So just you need to make a smooth tunnel, and no need to use any fuel, because the idea is to go from one end to other end. So gravity itself will take you from one end to other end. Now the difficulty is making the tunnel. So, but we can make the tunnel at least near the surface somewhere here, if not at this depth. So how the gravity will pull this train? So gravity will pull the train towards the center like this, isn't it? Because we are drawing Earth. So this will be the force. Let's say this is the gravity pulling towards center, and I'm assuming the distance of the train from the center is r. So now you can see the force will have a component along the tunnel which will accelerate. So what is the point of equilibrium? At which point there is no force? Exactly at this point, right? This is the mean position. Why? Because gravity will act like this, and it will have no effect to propel the train right or left. So if this is the mean position, and if I call this as x, if I call this as so if I displace from the mean position, what force will get? So if I call this force as F, then the net re-steering force is how much? The force which will propel F cos theta, and F we can write as mg cos theta, isn't it?
Yes,
You
sir.
can see the re-steering force is pretty easy, right? Mg cos theta, and m is m. G is we know the answer, 4/3 pi rho g r, because r is the distance from center, and then cos theta. Now, what is interesting here that no matter what is the r, what is the cos theta, the r cos theta is interesting. M is the mass of the train, right? What is r cos theta?
X.
X. So that is why the answer will have only dependency on x, and that's why this is going to be a SHM equation. And what is also interesting that here we are not taking any approximation; it is naturally coming SHM, which means if it is SHM, then what will not matter is the amplitude of oscillation. So no matter how big the tunnel is, the time taken to cross the tunnel is bound to be fixed. It is going to be same value, because if you calculate the time period, so what is the acceleration? Minus F restoring by m, because the m is the moving mass, and you can see that m will cancel out. What we get is only, and this is very interesting answer which we need to understand, that the omega square, let me write on this side, omega square turns out to be 4/3 pi rho g, and here nothing is variable, everything is fixed. 4 is a constant, pi is constant, 3 constant, density constant, g constant. So the entire time period is a constant value. 2 pi root. pi by omega, so we can add 2 pi by 4 by 3 pi rho g. And it's good to write 2 pi inside, so it will become 4 pi square 1 4 by 3 pi rho g, and 4 pi cancels out. So what we're getting is time equals to under root of 3 by pi rho g. No? 3 pi. No? What I'm writing. So 3 pi by rho g. This is the answer. And if you find the density of Earth and g value is known to us, this turns out to be how much? Just calculate the value. So Earth's density is roughly 5.51 gram per centimeter cube, or you can say 5,510 kilogram per meter cube. Just multiply by. So Earth is only 5.5 times denser than water, nothing much. So density is 5510, 6.6710 power minus 11, right?
Yes, sir.
So let me check how much we are getting the value. 5510. I will multiply by 6.6 into 10 power. So it is roughly equals to 1.4 hours. That's it. So what is interesting here? Interesting is that no matter which two cities you can join, making a tunnel, the time to reach the one city to other city will be half of this time, because this is the time between full one complete oscillation. But if you want to go from here to here, how much time it will take? Only 0.7 hours, because this is half time period, isn't it? Going from one extreme to the extreme is exactly half time period. Is this clear? Hello guys, am I audible to you?
Yes, sir.
So now this is a very ambitious project. So if you want to connect any city, and 1.5 hours is how many minutes? Just in 42 minutes, you can reach between any two city by making this tunnel technology. So that will be really fast. I mean, nothing can beat this speed, because even the hyperloop cannot beat this. So this is going to be the next future, and hopefully, maybe you guys will be working for this after maybe 30 40 minutes. I don't know. Right now, it's underway. I think Elon Musk has taken this task, and he is capable of doing anything like this. Now, there is something very famous question called pendulum, but in a different way. This is called like long pendulum. So this is the extension to the problem of simple pendulum. So what if the pendulum becomes really long? I mean, if if I draw this as Earth, this is Earth, then my bob is somewhere. You can imagine the length of the pendulum itself is bigger than the Earth's radius also. It could be possible. Hypothetically. Okay, I'm not going to make something like this. Maybe I can suspend a pendulum from the satellite and hang like this. Yeah. And we'll keep it just above the Burj Khalifa height so that it should not hit anything on Earth. Or maybe above the Mount Everest or the then of course highest peak in the universe. I mean in the world. So this is the question. Like this is an interesting question. Like if I do this hypothetically, and if I call this as radius as r e. So earlier we used to take the pendulum which used to be very small compared to the Earth, and therefore the things were easy to calculate. But what happens if we have a situation like this? Even if you tilt a bit, even if you tilt a bit, because of this large size, it will swing quite far away. This is angle is alpha. You tilt by theta, but now the gravity will not act vertically downward, right? The problem is the gravity will act this way. Can you realize this part? So this is how the gravity will act. This is how the tension will act. And this angle we can call it phi. So the tangential force, which used to be earlier mg sin theta, now this is not going to be mg sin theta, right? Why? Because earlier we used to draw mg like this. Now can we draw mg like this? The answer is no. So now the tangential force, we need to find this angle. I mean, now the whole idea is what is this angle? Let's call it alpha. Because to write the restoring force, what we can write? F restoring is how much? So it must be mg cos alpha, right? And this is 90. Now this is easy to find because you can write 90 plus alpha plus theta plus phi must be 180. So the alpha turns out to be 90 minus theta plus phi. This was less obvious now, but we can get this answer. Is this clear so far? Yes or no? So the restoring force is how much? Mg cos 90 minus theta plus phi, which is equals to mg sine theta plus phi. But as I said, we are only solving for the small angle, then only the system is possible. This is the general answer. So for a small angle, okay, first of all, the acceleration will be how much? Minus f restoring upon m, which will give you minus g sine theta plus phi. For a small angle, if theta is small, then phi will be equally small, not a big issue. And therefore, the A we can write as minus g theta plus phi. Now that's a very interesting change from the previous derivation. We can here call it x. And now what is interesting is we can write theta equals to x by L, the way you used to write earlier. But phi we have to also write, and the phi we can write as x by RE. That's the change. So the acceleration comes out to be 1 by L plus 1 by. And now if you compare with the minus omega square x, omega square turns out to be this value. And you can see the time period will have a very drastically different formula. Okay, it is clear.
Yes.
So we can take two cases. So the first case is like, what if L is very small compared to the Earth radius? If L is really small compared to Earth radius, then 1 by L will be much bigger than 1 by RE. So 1 by L plus 1 by RE is roughly equal to what? Tell me. If I add these two values, then can we equate by 1 by L? Hello, 1, 2, 3.
Oh,
Hmm? If 1 by L is much bigger than 1 by RE, then can we sum and we can call it 1 by L only?
yes.
So the time period will be how much? 2 pi under root 1 upon G. If you remember, the answer was 1 by L plus 1 by RE, but this will be as good as
L by
1 by
G.
G, 1 by L, which is, yeah, L by G. So I think that's
L5.
right. And this is exactly matching the formula of simple pendulum, right?
Yes.
So the simple pendulum formula is only true when L is very small compared to the Earth radius, else it is not true, which is significantly true when you can see this formula is saying the same. So what happens if L becomes much bigger than KS2? If the length of pendulum exceeds the Earth radius by large value, 1 by L becomes very small than 1 by R, and therefore the sum is as good as 1 by R, and that is where the time period becomes 2 pi under root RE by G. So these are two extreme situations. So for any problem in which if I tell you, okay, let's say we have a pendulum of length equals to RE. So if I say, let's say we have a pendulum, uh, if length of pendulum is equals to radius of Earth itself, then the time period will be 2 pi under root 1 by G into 1 by RE plus 1 by RE, right? Which is 2 pi under root RE by 2G. And so on. So you can keep on solving. So these are two extreme answers, and then we can have any answer in between. And a question on this may come in examination. So we are done with the gravitation. Which chapter comes next? Fluid mechanics. Huh? So we can do the SHM in fluid. So are we, I mean, done with the fluid mechanics? Yeah, I think so. Fluid is
Yes.
done. Yeah.
Yes, sir.
So SHM in fluid mechanics, and everything you can do from a scratch method. So let's say we have a water and we have a nice floating cylinder, and if the height of cylinder is capital H, but the submerged length is only small h, and if the area of cross section we can take as h, so this is in equilibrium. This is the h is the equilibrium depth. It is at rest. If this is the equilibrium depth, what does it mean? So if I dip further, what will happen? So the moment you slightly dip further, which force will grow in value? The bond force will grow in value, isn't it? So if you dip it further by x, the excess buoyancy will be the restoring force. So the restoring force is equals to extra buoyancy. And this is pretty easy. It's V area into cross section V rho G. And if the mass of the cylinder we take as M, this is the density of liquid. So the acceleration will be minus the restoring force upon mass, which is minus A rho G by M into X. Comparing with the standard equation of SHM, omega is under root of this, but time period is 2 pi under root M by rho Ga. But what is interesting that this answer can be converted into something more simpler answer. And if you convert, you will get something very interesting. So mass we can write as the density. Just a D is the density of object. So density into volume, which is A capital H, and therefore M by rho Ga is same as DAH by rho Ga. So what we get is D by rho into H by G. Now, if you remember the density of the submerged part upon the total length, this ratio is always equal to density of object upon density of liquid, if you remember. So D by rho itself is H by H. You can go and revise it. Eventually, it will be equals to only H by G. That's what I said. It is same like a pendulum, and in this pendulum, the length is replaced by the equilibrium depth. So you can always compare something like this and to remember the last answer. Even if you forget everything in the examination, just remember one thing that the answer is like a pendulum and the answer is like 2 out L by G. But what is L is here? The equilibrium depth. So without revealing solving anything, just find a small h in terms of the variables given and you can substitute with the answer. Is this clear? Understood?
Yes, understood.
So now you may get an oscillation of liquid in a tubes. Oscillation. So you can draw any shape tube. So I'll just do a random shape tube. So let's say just taking the V tube because YouTube is very famous. So I want to make this famous. And we have a liquid which is so you can see in the very beginning, the height up to which the liquid is filled vertically is small h. Okay, so this is the liquid field. The cross section of the tube is fixed. Okay. Now, if I push the liquid one from one side by x value, it will rise along the length by x value. Correct?
Yes, sir.
So the old level, you can see the level will decrease on the left side and it will increase on the right side. Just what we need to find is this length. That's it. So if I say this angle is theta, can you find this length? How much is this length?
So x sin theta plus x.
Very good. And that is the exactly extra vertical height which will create the restoring pressure. So here what we define is not the force, we define the restoring, delta P restoring. Like what is the extra pressure it will generate? And the answer is rho G delta
Delta
H. That's it. So the rho G x1 plus sine theta is the restoring pressure. So the force is simply pressure into cross-sectional area. So the restoring force is delta P into cross-sectional area of the tube, which I assume is constant, means same throughout, and therefore the answer is rho G A x1 plus sine theta. Now, to find the mass of oscillating liquid, because the entire liquid will oscillate, liquid, the mass of the liquid we can write as density into volume, which is cross-sectional area into total length, right? So, what is the total length, by the way? H plus H by sin theta, right?
Yes.
Isn't it? You can check now. So, the total length of the liquid is H plus H by sin theta.
Yes.
So, mass is density into volume. Volume you can write like this. So, we can write as the restoring force acceleration equals to how much? Minus force upon rho a small h. So what we cancel out? Rho a this entire thing. Okay. So what we get is minus sine theta x by h. Uh, G also. No? Yeah. Is this clear? Just check this out. I
Yes.
mean, mm, okay. So if you compare with the omega square x, you can get the answer. Omega square is how much? G sine theta by h, and therefore the time period is 2 pi under root h by g sine theta. Now, why this formula is interesting? Again, for U tube, theta becomes 90 degree. and that time period becomes 2 pi under root h by g. That's again a simple relation. Okay, is this clear?
Yes, sir.
Yes, sir.
So can you do it for the random V tube in which we have alpha, beta both angles?
Yes, sir.
Yeah, so do it. So we have to solve for the random V-shaped tube, but here both angles are variable, and liquid is filled up to vertical height small h in the beginning. That will help me in solving. So let's say the liquid is filled up to this height. So same liquid, not a difference. So you have to think about this is given as small h, and once you push the liquid from one tube and release, it will oscillate. And what is the time period of oscillation? So do this question. Tell me what you're getting.
Sir, I got answer.
Very good.
2 pi under root h by g sine alpha sine beta.
Correct. That's the right answer. And you can see that you can apply this formula for any question. So if it is U tube, then alpha beta is 90. If it is the tube which we drew earlier, it is 90 and theta. So if you keep on putting the value, you can get keep on getting the answers like that. Understood?
Yes, sir.
So so this is a fluid mechanics. We can go to other chapter. Maybe thermodynamics. So SHM thermodynamics. There's a very famous question, the jar problem. So let me make the jar first. So we have a jar with a neck, and probably we are going to assume the neck to be fairly small compared to the jar volume. So this is like the underlying assumption. And there is a gas filled in the jar. So, gas. And there is a small, maybe a pebble, which is stuck inside the neck of the jar. And this is free to slide because of frictionless. So you may consider external pressure, but that external pressure is going to be constant. So if I say of course, there is some external pressure for sure, and the mass of this pebble is m. So if you do the FBD, and if I say the cross-sectional area is A, the force acting downward will be P. I mean, let's say this is P gas, this is the P atmospheric. So we have the pressure from outside, which is pushing it down. So P ATM into A, and the gas pressure will push upward. So P into A, and gravity will pull downward. So just to show it, I'm showing. So for at equilibrium, what you can add? At equilibrium. So the PA is balanced by PATM A plus mg. So the pressure of the gas turns out to be PATM plus mg by A. That's obvious. This is called the equilibrium pressure. The pressure at equilibrium. At equilibrium. Let's say volume of jar is capital V, and the walls are adiabatic, which means the heat cannot enter nor exit. So heat transfer is not possible. That's why we call it adiabatic wall. So what we do next is we slide the pebble below, slightly below. Okay, so if you push it down, if you shove it down the pebble, it would compress a tiny volume. So if I'm pushing down by X value, so how much volume we are compressing? So the delta V is how much? Delta. Can we write AX, and of course you can put minus sign if you want to write the value. This is the value mod of delta. Is this clear so far?
Yes.
Yes, sir.
Now, any compression of gas will increase the pressure of the gas inside, isn't it? So earlier the pressure of the gas is P, but now when you when you pushing the pebble inside the neck below, will it change the pressure? Yes or no? Hello, hello, 1, 2, 3. So if I push the pebble below, so the gas pressure will increase, yes or no?
Yes, increase.
So if gas pressure will increase, then it will act as the restoring pressure, right?
Yes.
Yes, sir. Above. Yeah.
So now we are dealing with the restoring pressure, which is generated or developed due to the compression of the gas. Do you realize this? Yes or no?
Yes, sir. Understood.
Now, because this is the adiabatic process, because the heat exchange is not possible. So for adiabatic process, we know that what do we know?
Delta Q0 equals
Okay.
0.
So the bulk modulus, we define bulk modulus as. So okay, of course, for adiabatic process, we know that delta Q is 0, which gives the answer fairly known to us. But we are not interested in the answer. We know that PV power gamma equals to constant, or you can say ln P plus gamma ln V is constant, and so we can say that dP by P. And if you remember the answer, if you differentiate gamma dP by
Yes.
V equals to 0, and we have done all this thing in past. So the dP is basically minus P gamma by V d, and this is the restraint pressure. That's it. So you can see that any compression will create the restraint pressure. So the increase in pressure will be how much? So you can say delta P is minus gamma P equilibrium. Now when you see the P here, this P represents the equilibrium pressure. So this is upon volume of the container, and dV we can write as A into X. We are writing the value. Okay, and of course minus we can make it plus, because delta V is value wise AX, and pressure will grow in value because delta X is negative. Delta dV is negative. The compression, so change in volume is negative, so pressure will grow in value. This is the restoring pressure. Restoring pressure. Do you realize this? Yeah, okay. Is this part clear? The part of the restoring pressure.
Yes.
So rest is just laws of motion which we have to write, and we are done with the answer. So we can write what we can write. So delta P into A, which is the force, equals to mass of the pebble into acceleration, and you can just put the minus sign for the sake of value. Direction of acceleration is opposite to the displacement, so that's why minus delta P. How much we got? Uh, Gamma P AX by V. Gamma P AX by into A. Yeah. So the acceleration turns out to be how much? Minus gamma A square P by mv whole into X. This looks really dangerous, but it's very easy. No? Don't cancel. This is gamma. This is V. And therefore, if you compare with omega square X, So the time period will be 2. And if you want, you can replace by mg gamma a square, and p at equilibrium was p atm plus mg by a. Now you can take one special case. If special case, if p atm is 0, then the answer will be really nice. The answer will look like simple 2 pi under root v by gamma a g. So if I want to define something like L effective, what is L effective here? So you can always add this as 2 pi under root L by the effective length upon g, which is like v by gamma times A, right? So question like this can be, I mean, created in the examination, and we should just apply the thermodynamic process. If it is polytropic process, then it will have some other exponent. Is instead of gamma, it will have something else. But the whole idea of like applying SHM in thermodynamics is try to understand the delta P to various relation, and once you have the restoring pressure, multiply with the area of cross section to get the force, and from there you can derive the other relation. Okay. So which now every chapter will have a system, like electrostatics will have variety of question of system, then magnetism will have, electromagnetic induction will have, in fact the atom, the nuclear physics also will have something. So the whole idea is the rest will study in the pertaining chapter only, so not now, because these are the chapters which you have already covered. So these systems we should know, but there is no chapter which is without SHM, because every chapter will have force and torque and so SHM. So learn the basic idea that how we approach, not the formula. Of course, certain questions can be solved by certain formula, but that will never help you in the J advance. Other examination, yeah, it will help, but not in all exams. So I think we have done with the superposition also, right? In the very beginning only. Do you remember?
So which?
Superposition theorem? Like adding multiple SHM mathematically?
Oh, yes.
In the very beginning, like if you have multiple sine function, then you can graphically add like a vector.
Yes.
So that was the one part which is
Yes,
the
sir.
most important, and just revise that part. So we are done with the chapter of SHM. So this is the end. Let me see if I have left something from the previous.
Sir, but we didn't do the addition.
Pardon?
You we didn't do the addition part. You taught how to find the time period for each for trigonometric function.
Yeah. Okay. Yes, that one. Yes. So that is called the superposition theorem. So if that is clear, then nothing is left. So the alternating current is a chapter which is quite similar to the. I think okay that I did in the alternating current, not here, no?
Yes, sir.
Ah, right. So let me do it here now. Just check if anything I have left. There are two things which I believe I have left, but maybe if you come across, you may ask in doubt. Okay. Hmm. There are a variety of questions that we can solve. There are two things are remaining, which is called the damped oscillation and forced oscillation. Yeah, that is very crucial for JME, so we have to study. Okay, so that will cover in the next lecture. Yes. All right, so we'll take maybe 1.5 lecture, maybe half lecture in the next. That will be end of the chapter. I'll cover the SHM superposition once again because that is something. Okay, now I realize that I discussed in the chapter of alternating current, but those who have not attended that session, uh, there are two things. You can watch that video, and that will be very good because that I have covered in detail, or I'll cover in short here also.
Sir, that sign two different,
Yeah, yeah. Yes. An addition of two different sinusoidal functions. That's it.
and then we have to calculate the time period of.
No, not time, but calculate the net amplitude, the new amplitude.
Yeah, sure.
I mean, I think you don't remember this, but you can go back and you can just search for it. Okay. So, okay, I will not do the end. This is incorrect. So we'll just add a few more things and we'll wrap up. So by next lecture, we'll end this chapter also. We'll start the wave and sound as well. So we'll do two things together. All right. So don't miss the first lecture of wave and sound. If you miss it, then the wave and sound chapter will be nightmare for you. But if you start just attend the first two lectures, then you can master it. Because all the theoretical detail I will cover in the first lecture. It will be mostly a verbal lecture. So I will not be writing anything much writing. So you have to just listen to all the philosophical thing, and then afterwards the chapter is pretty easy.
Sir, that part in this chapter where you added two sinusoidal functions, sine
Yeah,
theta,
yeah,
sine theta, and this is
correct.
find the time period like 2 pi by if it is like sine theta and 2 pi by 3. So I
If
didn't
it is
understood that.
okay, you just leave this part. So you can ask me in the next lecture. Okay.
Yes, sir.